Good evening, everyone. So we will be starting the class soon. Okay. Yeah. So last class, I hope you remember where we had stopped. We were looking into the assignment problems, and we were looking at how the impedance model will be if we are taking into consideration a porous electrode. Then before that, we saw constant phase element run on. So I'll just give a brief description about what we saw and then start today's class. Okay? Yeah, so we were looking into constant phase element. So ideally, when we are trying to plot a double layer capacitor behavior, when we do impedance, what we'll be getting is a typical semicircle, right? But in reality meaning in some cases when we are doing the impedance, what we'll be getting is not a perfect semicircle. Instead, we will be getting a depressed semicircle. We'll be getting a depressed semicircle. So this is called the constant phase element. And we saw that the value is equal to 1 by j omega c. And the omega value, sorry, this value, where we have, this is the case where we're using capacitor. But when constant phase element come, we get 1 by y naught, which is y naught being similar to the capacitance constant, and j omega raised to n. The n value can be varying like 1, -1, or it's an intermediate value. So then we looked into the reason why we are saying constant phase element, because we said there is a roughness, and then each point results in different behavior. So that is the reason for the constant phase element model. And then because current distribution becomes different in different points. Then after that we looked into some of the models that we are using in order to calculate the double layer capacitance behavior when there is what to say, yeah, this depressed semicircle coming, and we said it's Hamanfield's the formula, and also we said it's Bragg formula. Then after that we moved into porous electrode, how the derivation is coming. So we have a porous electrode, and in which there are pores inside of zero. We are saying it's equal to zero, x is equal to L, and how we're giving boundary layer conditions and trying to derive it. So what we say that the pores are actually cylindrical, and we're considering only metal electrodes, and there is the same potential occurring across every point, even in the walls. Axial diffusion is across the axis, the diffusion is neglected. And then if an ideal capacitor behavior is then assumed within the pore, then the specific impedance of the pore wall electrolyte interface is given by such an equation, which is written over here. So where which is due to static impedance as well as the double layer capacitance behavior. Then after that, we are concerned there is no impedance. Faraday impedance is infinite, and then we derive the equation. Finally, we are also giving the boundary layer conditions. Applied potential becomes equal to, I mean, it's EAC not at the entrance, and the exit there, it becomes a constant. And then we derive the expression for the potential inside the pore like this. You need to know this equation. If we then simplified it, and finally we also got the expression for current. Then we got the impedance of the pore. Yeah, so that's what we were looking in the in this class. So being the last class, I'll be trying to just wind up many of the things, so I'll be a little fast. So let's move on to assignment number 9. Okay, so I'm not wasting time, so directly I'm going to the questions. The question number 1 being, Consider a system which exhibits constant phase element behavior given R solution equal to 100 ohm centimeter square, RT equal to RP equal to 200 ohm centimeter square, and CP parameter y naught equal to 5 into 10 to the power minus 5 ohm inverse centimeters inverse square s to the power n, where n equal to zero point 0.8. We have to find equivalent capacitance as per Bruck's formula is dash microfarad centimeter square. So this is the question. So we have to use the Bruck's formula. So the question is, what is Bruck's formula? So we saw in the last class. Okay, we are supposed to write it in this one, class 13, but I'll just finish this one here. So the Bruck's formula using, yeah, Bruck's formula, when we are using, the formula becomes the double layer capacitance effective equal to y naught raised to 1 by n 1 by r solution plus 1 by rt n minus 1 by n. This is the equation. So y naught value is 5 into 10 to the power minus 5, 1 by zero point 0.8, 1 by 100 plus 1 by 200, zero point 0.8 minus 1 by zero point 0.8. So please solve it, we'll get the answer. Just let me try solving it. Yeah. So I'm getting an answer as 12.01 microfarad per centimeter square. So the given answer is between 11 and 13. So this is the right answer, expected answer. Now let's go to the question number 2. Okay. Consider a system which exhibits CP behavior given R solution equal to 100 centimeter square, ohm centimeter square, RT equal to RP equal to 200 ohm centimeter square, CP parameter y naught equal to 5 into 10 to the power minus 5 ohm inverse centimeter square inverse s raised to n seconds raised to n value is 0.8, and the question is equivalent capacitance as per Fusu and Manfield formula is dash per farad per centimeter square. So you're supposed to get a value between 15 and 17. So how do we solve it? Let's write the Mansfield formula first, which is CDL equal to y naught raised to 1 by n RT raised to 1 minus n by n. This is the formula. Let's substitute the value. So let's find out the answer. Please solve it. Yeah. So once you're solving it, I'm getting 1.5811 10 to the power minus 5 farad per centimeter square. So it becomes 15.81 microfarad per centimeter square. Okay. So now let's move on to the third question. So the third question is as follows. In the same system, if y naught equal to 2 into 10 to the power minus 5 ohm inverse centimeter square inverse second raised to n and effective capacitance, our solution RT, RP are same as before as per Braggs formula. Value of n is so in the previous question you have to take the values as before. So as before meaning the question in which we are using Braggs formula. So that's like the first question we did. I solved it here. It is 12.01 microfarad per centimeter square. So CDL is equal to 12.01 10 to the power minus 6 farad per centimeter square. This from question 1 in this assignment. Okay, because they have told Braggs formula, I'm taking that same value. For that question, what is our solution? 100 ohm centimeter square. What is RT, RP? 200 ohm centimeter square. Now substitute all of this, find out using the Braggs formula, which says CDL equal to y naught raised to 1 by n, 1 by r solution plus 1 by RT raised to n minus 1 by n. So how to solve this question? If you say 1 by n is in common, or else try trial and error or use a software, some mathematical coding, try to find out the n value. So if we solve it, we will get n values 0.928. In the question, it's between 0.92 and 93. So it's correct. Question 4 says CP behavior may be expected when electrode has 2D heterogeneity, 3D heterogeneity, both of the above, none of the above. So what's the answer? So CP is arising because of heterogeneity, be it 2D or 3D. So the answer is both of the above. Okay. In a given system, EIS was acquired at different DC potentials. Double layer was described by CP as potential increase the magnitude of CP parameter Q increased. The exponent N is expected to increase, decrease, remain constant, is related to Q. So how to solve this question? So when we are decreasing the value of magnitude, so when we are increasing the potential, we are here seeing that and the magnitude of CP parameter Q is also increasing. So we can expect that in this case, the exponent value will be decreasing. That's the answer. Now question number 6. Consider a porous electrode EDC equal to 0 volt versus OCP, and there is no reaction when an AC potential is applied at the pore end. So these are the options. So we saw when we are considering the force at x equal to 0, x equal to L. Here we say applied potential equal to AC naught, and here dE by dx equal to 0. So the option is A, where potential grade. So these are the boundary layer conditions we are applying. It's direct question. If you know the derivation, you'll be able to answer. Now question 7. In the above case, electrode has 3 into 10 to the power 6 volt per centimeter square, each of 1 micron radius, and with 400 micron pore length. And conductivity of solution is 15 centimeter. Our solution equal to 10 ohm. Calculate the total resistance of the solution in a single pore. So this is the question number 6. Sorry, question 7. So just because it's written on the last page, I'll just write again. 3 into 10 to the power minus 6 4 per centimeter square. Radius equal to 1 micron. Pore length equal to 400 micron. CDL equal to 20 microfarad per centimeter square. So what is the formula? So if I see the formula becomes 15 ohm centimeter, I repeated ohm 400 into 10 to the power minus 4 centimeter by r square. This writing r separately, 1 r, this 2 r. Now if you solve it, find the answer. So once you solving it, you will get 19.01, sorry, mega ohm. Okay. So now next question. The above case, calculate magnitude of dimensionless admittance of the port at a frequency of 1 hertz s dash ohm inverse centimeter square. So here the formula becomes to find the dimensionless admittance. The formula is YCDL 2 pi RL rho L by pi R square. So if I solve it, here the Y naught value is 20 microfarad per centimeter square. This becomes 2 pi, so pi and pi goes R and 1 1 R goes. So it becomes 2 L and L. There are L square. Density is given as, sorry, you have the conductivity is 15 ohm centimeter. The whole by 1 into 10 to the power minus 4. So here it is the double layer capacitance value, so it is j omega. So now you have to find out at 1 hertz what is its value. So it's already root, and within the root there is another j. So please solve it. You may need some software to do it. So you can do this alone and find out the answer, but this is how it is done. Now next question is, in the above case, if our solution is equal to 100 ohm, calculate real and imaginary power of impedance of electrode at frequency of 10 hertz. ZRE equal to dash ohm centimeter square. And the next question is to find minus Z imaginary. So this one, again, you may need to have this code. So you have to solve it, find out the real part and imaginary. You need a software to do. I think the next part of questions also, basically it's like your real part is given, and then you have to the real analytic frequency of zero point 0.1 hertz. The next question is, so this is at 10 hertz. The next question is zero point 0.1 hertz. What you will get for the same conditions. So I can give the answer, but you may need some software to do it. So this I was getting 102.1, and this was 10.63. Now when zero point 0.1, this becomes 102.12, and this I was getting 1055. So these are the values I'm getting. Probably you'll need to use some software in order to compute the same. Okay. So now, next one, we are going to look into films and PDM, point defect model and films. So this, before that, just giving a brief introduction about what exactly is there. Then we'll look into the problem. So basically from this, um, I mean, assignment number, it's fully, what to say, theory type questions. So you don't need to worry. So giving a short, what to say, an insight about what this is, and then we'll continue. So that's how I can move forward. So you have to first look into film formation and passation. So when there is a film formation that's happening on the surface of the electrode under study, you will see that the impedance in the EIS, right? Impedance response changes of the electrode. Now, this depends upon the nature of the film, which again depends upon the nature of formation and also on the film content. So, film content means this can be organic. So, organic means it's deliberately introduced, like adsorbed and formed on the surface. Now, this can also be inorganic. Inorganic means it is metal oxide. So, where it's reacting between the electrode electrolyte interface. Um, so, yeah, like the which is reaction between the electrode and electrolyte. So, when metals like what to say, aluminum, it reacts with the electrolyte, it forms a passive hydroxide formation. So, those all comes over here. So so to describe this to use impedance modeling, they use different models for each case. So that's what we're going to look into in this case. So we look into the models which are employed. So first one will be film, which is a perfect insulator. So what is a film insulator? It can be also non-porous. I can say this is non-porous. If it's porous, it will allow the liquid to pass through. So it's a perfect insulator only when it's non-porous. So when it's non-porous, what happens? It blocks complete electrode surface. So this is the case. You have the electrode, it's insulating, non-porous film. And then you have the electrolyte. So it wouldn't allow the electrode light to penetrate it. So because they are, well separated, I can use a model where this will have a capacitor. So there is electrolyte. Let's start from there. So when this is in contact with the electrolyte, it will create an R solution. Then it will have the electrode will have a double layer capacitance. And apart from that, there will be film which is having a capacitance behavior. So this is the first model I can say. So here we can say that the film is described as a capacitor which is in series with the double layer capacitor of the electrode itself. So and also there is a solution resistance when the electrode is immersed in the electrolyte. So basically it is a sum of CDL and the film capacitance. So if you see there is two double layer capacitor and one solution resistance. If I see this solution resistance is a simple point Now, how will the double layer capacitance be? It is kind of blocking, right? So in this, so it's gonna be a single line which is vertical, which shows that it is blocking. I cannot say completely, like initially it can be something like this probably, and then it becomes a straight line, especially at the low frequency regime. So in this case, the RCT value is going to be very large. So like extreme cases, it can also go to infinity. So in case the film was heterogeneous, we can replace the film capacitor by CP. That is also possible. Second one is film insulator with same porosity. You have an electrode, have an insulating porous film, and you also have electrolyte. You have something of this can be modeled using. I'll draw first and then explain. So this entire thing can be plotted, I mean drawn using this. And in this becomes because of the film. Because once it's in electrolyte, then after that this part where the electrode electrolyte is there, this can be plotted using the double layer capacitance, and you have CDL, RT, and this the Warburg. And within that, you'll also have another R. So this is how the plot will be coming. So this is having some porosity. Some porosity means it is allowing some electrolyte to pass through. So this means some current is passing. And the capacitor with R, this one, it is in parallel with the parallel model with film. So this capacitor with R will be modeling the film. The capacitance, it's depending upon the double layer capacitance of the film and the thickness. Now the complex plane will have two loops, one for the film and the other for the double layer. And if there is a mass transfer limitation occurring, we'll also add an additional Warburg close to the RT of the double layer, as we are seeing here. So conducting film and moderate dielectric constant. So there is a conducting film and moderate dielectric constant. So this means this assumed to have no porosity. So it has electrode. You have conducting film, but it's not porous. This is electrolyte. So see here it's like it's having porosity. So it's kind of interlinked or something I can say. But here this is separate, this is separate. So when I draw, this goes to the film and at the at the interface of the electrode with the electrolyte, which is nothing but the interface of the you will have RT and there is an R solution. So this one is then modeled using this. So this is what is conducting film. So because you see it is conducting, but it is not porous. So we cannot say that both are together. They access separately. So the next one you have to look is into the point defect model. So when you have a film that is formed by the electrode oxidation, and if the film is continuous, that is it's not porous, and it is not dissolving into the electrolyte, it is offering some sort of passivation. Many such films, like over the time, they'll be losing the passivity in the presence of like the chloride ions and etc. And this is because of the pitting process. So this pitting needs to be explained. How can we do that? We can use the point defect model. So describe the pitting corrosion. So this is described by Digby model. So point defect model is to describe the pitting corrosion. So this is giving some sort of description to the process which is happening at the metal film electrolyte interface. So film is covering the electrode surface, and the film is basically made of metal oxide like aluminum and seawater or magnesium and seawater hydroxide formation. That is a metal oxide. So metal, so the film is a lattice. So which is not, so it is a lattice and it's not perfect in nature. So which means it will have both the cation and anion vacancies. And this can also have some cation interstitials. So anions are very large, so they cannot form the interstitials in the film very easily. So this totally involves seven processes. So first, so like by what mechanism the film formation is proceeding. So that can be described by different mechanisms. So the first one can be like cation interstitial generation. So here there is a metal which is going from the metal film into the so there is a metal atom M. So which is going to cation interstitials. So it becomes something like some ions it's becoming. So this is causing some vacancy in the metal, which I say vacancy in metal is mu M. And this will also release chi electron. So this will be contributing to current, and this is not causing an increase and decrease in the film thickness. Like doesn't it's not increasing or decreasing the film thickness. Like it's not causing film formation or destruction. So it's kind of conservative reaction. So I have the metal, it becomes M chi plus the vacancy plus electron. So it is assumed that the metal vacancy can diffuse quickly into the bulk metal, and they're consumed in a large sink. So there is no accumulation of the vacant metal sites near the metal film interface. So if the cation interface diffusion in the metal is slower than that in the film, we can then say that there's a thing happening in the metal. So the next one is cation interstitial consumption. So here the cation interstitials are there diffusing through the film. They reach the film solution distance. So here the interstitials are they crossing the interface and they're moving into the solution. Previous case it was staying in the film. The next one is a case where they're moving into solution. So it's some kind of oxidation state like chi plus or a higher oxidation state is happening. So, if the dissolution is oxidative in nature, then we can say that the current is generated. So, here also, same like before, film thickness is not changing. So, like there's a continuous supply of this happening. So, it goes from the interstitial, it goes into the solution. So there's a reaction that is happening. So the next one is cation vacancy generation. So there is a movement of the cations which are happening from the film into the electrolyte at the film electrolyte interface solution surface, and this is resulting in the formation of the cation vacancy in the film. So there's a case when it goes to solution, obviously there's a vacancy. The cations which are there in the film, they can either oxidize further, or so oxidizing further means it goes from this state to that where it's in the solution state when it moves into the solution. So this resulting in the current, which is like continuation of the previous case. Now the oxidation state in this case is not changing, right? So in that case, there is no current associated with the step. So this kind of a lattice conserving type of reaction. Next one is cation vacancy consumption. So the previous one was vacancy generation, and now what if that vacancy is getting consumed? So vacancies are created, they are diffusing through the film, they are arriving at the metal film interface, and they're getting consumed. So here it is assumed that the metal vacancy is continuously diffusing into the bulk metal and they consume the large sink. So there's also a lattice conserving reaction. So till now we were talking about the cation vacancy creation, vacancy consumptions, vacancy generation, etc. Now let's consider the case where anion vacancy. So what is happening here is the metal atom which is near the metal. So metal atom which is there near the metal film interface, they are oxidizing and they are becoming cation. Okay. Now this is resulting in the formation of a metal oxide. This resulting in the formation of a metal oxide with an anion vacancy generation. So this can contribute the current. So I'll repeat once again. So you have metal atom which is near the metal interface, metal film interface. So this oxidizing and they are forming a metal oxide. This is accompanied by the formation of a vacancy of anion, and this will cause the continuous thickness increase of the film, and this is a non-consuming, like non-conservation reaction. Now, finally, your cases. So, anion vacancy consumption is like the anion vacancies are generated in the metal. Anion vacancy is generated in the metal film interface, and which is diffusing through the film and they are reaching the film solution interface. Now, here what is happening is it's reacting with water and they are filled with oxide anions. So they get essentially consumed in consuming the they will essentially finally they will consume the anion vacancies. So if I say this is 2H plus which is released as byproduct. You have the vacancy, it's reacting with the water, it forms the H plus side, the vacancy, and this is occupying the vacancy side. So this is lattice conserving. Now you should also consider the case of film dissolution. Film dissolution is like the metal oxide is getting dissolved at a particular rate, and this depending upon the solution composition and the film content. So it becomes MO chi by 2 plus chi H plus. So if the oxidation state of the cation in the film chi plus, it's different from the solution species, it can contribute to current, but if they're of the same state, it won't contribute to the current. So this kind of film consuming reaction, it's non-conserving in nature. So basically, the cation and anion interstitials, cation interstitials and the anion mechanism, they're created in the metal film interface. They are getting consumed in the film solution interface. That's the difference you have to understand. And you'll have the cation vacancies which are generated in the film solution interface. So this is what you have to understand about the films. Now let's look into assignment 10. So because of the time limitation and I want to discuss about the next assignment also. I'll be reading out the assignment 10. Okay, that's how I'll be discussing this. So if the porous film, okay, well, let's look into this. If porous insulating film is present on electrode surface, film component may be modeled with option A, option B, option C, so you have a porous insulating film which is present on the electrode surface. Film component may be modeled using. There is a film. So obviously, it cannot be a resistor, it cannot be a capacitor. Either capacitor in parallel with resistor or a capacitor in parallel with series connected resistor and Wattburn. So it's already told it's insulating. So if it's insulating, nothing can pass through. If nothing can pass through, you need not consider mass transfer limitation. So the open option directly becomes capacitor in parallel with the resistor. Just give me a moment. So now let's look into the next question. A perfectly insulating film on electrode surface is modeled as. So if it's perfectly insulated, nothing happens, then it can be modeled only using a capacitor. And this is the answer. In point defect model, the two types of defects are vacancies and dash. So we looked in the last case, I mean first case and all, it was interstitial. This is the answer. Point defect model describes various processes that can occur in a film on the electron surface. As per PDF, anion vacancies are produced at. Where are the anion vacancies produced? So that was the last point we had discussed when I was giving the summary of that portion. So where are the anion vacancies usually found? So vacancies are happening at the metal film interface. So any consumption, that I mean dissolution. So basically the cations, they are I mean consumption and all happen dissolution to the electron. So that's happening in the film solution. So the vacancy resulting from that, it's happening in the metal film interface. As per PDM, so that's the answer question to the answer that I told previously. So where are the cation interstitials consumed? Same option as before. So the vacancies, annual vacancy on all happens in the metal film interface. But where is it get consumed once it goes into the solution? So it should be in the film solution interface. So the next question is, During the anion vacancy formation, the film thickness remains constant, true or false. So no, so there will be change, like it's gonna change during the formation of the vacancy. So that's what is so that means so it's false. Now the next question is question number 7. Across metal film interface. As per point defect model, the potential drop across the metal film interface, it's depending upon film thickness, pH of solution, both of the above, none of the. So if you have a potential drop, obviously when the film thickness changes, the potential drop is going to change. Again, depends upon the pH of the solution, which will determine the film formation. So, which will again affect the potential drop. So it is both of the above. PDM employs the following equation to describe mass transfer in film. So PDM is employing which of the equation to describe the mass transfer? You have fixed second law, both in 1D, 2D, then Nernst Planck equation and the Fromhold equation. So fixed laws, they are corresponding to diffusion. Nernst Planck, it has diffusion, convection, and the what to say, electron neutrality, basically the migration. So the answer is Nernst Planck. Now PDM employs following assumption to describe mass transfer within film. Film is continuous medium. Film is lattice. Film is porous. Film has accumulation near interface. Accumulation of ions. So for this, they are considering film to be a continuous medium. Only then, I mean, you can apply a uniform kind of equation across the film. So they consider it as a continuous film. So the last question then. I'll write on the question and then write. So when you have a film which is present on the electrode surface, when you're having inductive loop at the mid frequency is seen in complex plane plot of EIS data, then which can be used to describe it. So the answer is SC and AIC. Basically, it has multiple option. So PDM is not accounting for the inductive loop. So other two I'm saying as the correct answer. So the next topic is a nonlinear EIS. So I'll be giving us brief summary about the nonlinear EIS and then moving into this. So the summary is going to be kind of quick so that we don't waste much time and we can wind this up. So give me a moment and then I'll come back. So if you have an impedance and in impedance if the system is not linear, so we have already looked in the session 2 what linearity is, what non-linearity is, and what are the sufficient conditions, etc. You can refer to that. So when you have the system being non-linear, then del E by del I, this is not impedance. So in this case you can use Taylor, Bessel, or any numerical method not to solve. Example becomes for linear y equal to 2 plus 5x. If I give this as linear, this is linear. I can say y equal to 4 plus 3x cube is equal to non-linear. So in this case, how to solve it? So if in case your x is equal to sine omega t, which is the input, your non-linearity can be solved by 4 plus 3 sine omega t to hold the cube. Okay, so you know what sine cube x is. You have to give the same substitute 3 sine x minus sine 3x by 4. So this is the what to say. You have to give this as substitution here, and then when you derive it, whatever you get, that is the linearized form. So that's how you have to solve this, or how you have to proceed with such a question. Now, you have to also know at fundamental level, your impedance is equal to EAC naught by IFAC, and the unit is ohm centimeter square. But at higher harmonics, it will also have something like this. So here I can write in a different way. This is at higher harmonics. Here the n value equal to 2, but the unit is not equal to ohm centimeter square. So this is the difference that comes when it's non-linear. So impedance is not actually by impedance, it's expressed in terms of current when it's non-linear. So if it was linear, so other equations, they're remaining the same. We'll actually go through the questions directly so that we can have a discussion if required. So the question be, Consider modified Bessel function of first kind. The value of y at x equal to zero point 0.5 and n equal to 1 is how much? So basically, you can use the code or some sort of software where you can solve this. So when I solved it, I am getting the values 0.2579. Okay, so that's the answer. And the next one, Taylor series expansion of sine 3x is given by. So this we know directly. The options are so we already saw like in the here the equation is 3 sine x by minus sine 3x by 4. So option B. Now the next question, when EIS is acquired experimentally, it is desired to sinusoidal perturbation and acquire data after some time because would be steady periodic, the noise will be less. Both of the response, none of the above. When EIS is acquired experimentally, it is decided to apply sinusoidal perturbation and acquire data after some time. So is it because system would become steady periodic or because noise will become less or both of the above, none of the above? So in this case, you know, noise has nothing to do with the time you provide. So if noise is there, it will continue through the system or it may come and go. So what can be the option? If you are giving some time so that it becomes periodic. Initially it can be non-periodic, after which it stabilizes. So the option is system response would be steady periodic. Now question 4. When EIS is acquired experimentally, it is desired to acquire data for multiple cycles because system response would be steady periodic. Signal to noise ratio will be better. Both of the above, none of the above. So, when we are connecting EIS, like we have to do multiple cycles. Why is it decided? Signal because system response will be steady periodic. So you do single cycle or multiple cycle, it will take some time to stabilize. So it has nothing to do with the stabilization. Irrespective of that, it will take some time to stabilize. So next option is signal to noise ratio is better. So in the previous example also I told the noise is going to be the same irrespective of whatever time you give. So sometimes the noise can make the data something like this. Next time it can be so when you average it over time, you can get rid of the noise or you can minimize the noise or it can give better confidence. So that's why signal to noise ratio will be better. Okay. Now, for a given system, when perturbation amplitude EAC naught is increased, nonlinear charge transfer resistance will increase, decrease, increase, or decrease will remain constant. So we know that when your perturbation amplitude, we are changing it, or when you're increasing it or decreasing it, I mean, your after a period when nonlinearity is coming to play, it wouldn't be same as that of the previous one. So you can remove, it will be constant. Then it can either increase or it can decrease. It is not depending upon like what perturbation it gives nonlinearity. It doesn't say that your charge range increases or decreases. So the option is increase or decrease. Now, the next question is for a reaction with one or more intermediates, given perturbation amplitude amplitude of oscillation in fractional surface coverage decreases with frequency. Increases with frequency. Can increase or decrease. Independent of. So for a reaction with one or more intermediates at a given amplitude, the amplitude of oscillation in fractional surface coverage decreases with frequency, increases with frequency, can increase or decrease with frequency, or is independent of the frequency. So the option is it decreases with the frequency. Now, a given electrochemical system shows a DC current at a given DC potential when an AC perturbation is applied. The average current under steady periodic addition will be same as IDC. True or false? At a given electrochemical system shows a DC current at a given DC potential. When AC perturbation is applied, the average current under steady periodic condition will be same as IDC. No, it's going to be different. So the answer is false. For a given reaction, impedance under pseudo galvanic mode can be calculated using Taylor series expansion, Fourier series expansion, numerical method, all of the above. So here the answer is numerical. So now let's look into the last one also. So that's more on Trumkin, Temkin, nonlinear EIS, etc. Yes, but I realized that the last date for discussing this assignment is yet to come. So probably I won't be able to discuss it now because the due date is actually day after tomorrow. Sorry, it's after this week on 15th, right? So probably I'll discuss it if possible after that. But then, yeah. So then with that, I think we've come to conclusion by discussing all the questions up to assignment 11. Okay. So yeah, that's all for today. Thank you all. Thanks for joining.